In this video, I'm going to talk about resistivity logs. Resistivity log is one of the most important tools that we use in the logging. And using resistivity data, we are able to identify hydrocarbon saturated zones. In addition, we are able to have some estimates about the water saturation in the formation. And also, we may have some assessment about the fraction of producible hydrocarbon in the reservoir or recovery factor. Okay, now just let's look at Archie's law. If you look at Archie's law, I mentioned before that there are two important parameters in Archie's law. One of them is SW, or hydrocarbon saturation in the virgin zone, and the other is SXO, or hydrocarbon saturation in the flush zone. And in order to obtain SW, we need two resistivities. One of them is RW and the other is RT. RW is a resistivity of formation water, and RT is the resistivity of the virgin zone. And then for SXO, we need again two resistivities. One of them is RMF, or the resistivity of mud filtered, and the other is RXO, or the resistivity of the flush zone. And as you're going to learn here, using resistivity logs, we are able to obtain these four important resistivities. Indeed, there are two different logging tools that are available, resistivity logging tools. One of them is developed for non-conductive drill mud, or in cases where drill mud is made from fresh water. And that is SFL, Dual Induction log. SFL stands for Spherically Focused log. And as you see here, this logging tool is a combination of two individual logging tools that are put together, and we're going to have one entire resistivity logging tool. And then we have another resistivity log, MSFL dual ladder log, that is used for conductive drill mud. So what I mean by conductive drill mud, it means that when we make drill mud from saline water or brine. And again, as you see here, this logging tool is a combination of two tools. So one of them is MSFL, or Spherically Focused log, and the other is dual ladder log. In this video, I'm going to just focus on SFL dual induction log. So as I mentioned, this logging tool is a combination of two tools. One of them is a Spherically Focused log, or SFL. The other is dual induction log. Okay, so you're familiar how we are able to estimate resistance. For example, if we have an object, and then if we measure current and then voltage over current gives us resistance. And then from resistance, if we have some idea about the area and the length of the object, then we are able to obtain resistivity, that is the property of the materials. And this is a kind of how we are able to measure the resistivity of different objects directly. So what we need to do is just connect the object to electricity current and measure the voltage. And then we are able to estimate resistance, from which we can estimate resistivity. But here, just let me ask you a question. Is it possible to measure the electrical resistivity of an object without touching it? So in other words, as you see here, conventionally we can connect an object to current. So is it possible, even without connecting the object to an electric current, we measure the resistivity of that object? Is it possible? Yes, this is possible. As indeed, how we are able to do that, using electromagnetic induction. So what is a electromagnetic wave? If we have a electric charge, as we know, we're going to have some electrical field in the vicinity of that charge that is indicated by E. But assume that we're going to move this charge up and down, oscillated, and then what's going to happen, in addition to this electric charge, we're going to have at the same time a magnetic field as well. So in addition to the electric field, we're going to have a magnetic field, and that magnetic field is perpendicular to the electric field. And indeed, this produces a wave that is called electromagnetic wave. So whenever we have an electric charge that oscillates, it's going to produce electromagnetic wave. What I mean by electromagnetic wave, we have electric field and magnetic field at the same time, and then magnetic field is perpendicular to the electric field. This shows how electromagnetic wave propagates into a medium. As you see, this is the propagation direction, this arrow. And what you see here, the magnetic field is perpendicular to the electric field, and both of them are perpendicular to the wave propagation direction. And indeed, electromagnetic waves can be explained by Maxwell equations. And what you see from Maxwell equation, it says that so whenever we have a change or time variant magnetic field, we're going to have electric field. At the same time, if we have a time variant electric field, we're going to have electric field, we're going to have magnetic field, and vice versa. And using these four equations, we are able to characterize electromagnetic wave propagation in a medium. So I showed you before electromagnetic wave spectrum. As you see here at the bottom, it shows the electromagnetic wave frequency, and at the top you see the electromagnetic wave wavelength. And we know that for electromagnetic waves, frequency is linked to wavelength using this equation. C is the speed of sound, speed of light, and lambda is the wavelength. So what you see here, this arrow, just let me highlight it. This arrow shows the wavelength, and the bottom arrow shows the frequency. So as we see here in the nature, we deal with a wide variety of electromagnetic waves. For example, magnetotellurics is a kind of low-frequency electromagnetic wave. The frequency may vary from about 0 Hertz to 1 kilohertz. Then after that, we have radio waves that has a frequency in the range of kilohertz. And then we have GPR, or radar waves, that has a frequency range in order of gigahertz. And then we have visible light, X-rays, and gamma rays. Indeed, in geophysics, what we mostly use radio waves, the frequency in the order of kilohertz, to estimate the resistivity of materials in subsurface. So how it works? So if we produce an electromagnetic wave in an object, then it's going to produce an eddy current. So assume that we have a coil on the surface that produces electromagnetic waves in order of kilohertz. So what's going to happen if we have an object below the surface? You see that eddy wave is induced in that object, and as a result of eddy wave, we're going to have a secondary magnetic field. And by measuring the secondary magnetic field and primary magnetic field by another coil that is receiver coil. Okay, so this coil is the transmitter coil that produces the primary electromagnetic waves, and this coil is receiver coil that records both primary and secondary electromagnetic wave. The secondary magnetic wave, as I explained, is the magnetic wave that is induced or produced as a result of eddy current in a conductive object below the surface. Just let me explain it here whether. So assume that we have a conductive plate here, and we suspend a coil above the plate, and what we do next, we connect the coil to alternating electricity. So what's going to happen, we're going to have a time variant magnetic field, and that time variant magnetic field induces eddy current into the conductive plate. And from that eddy current, a secondary magnetic field is produced that is perpendicular to the initial or the primary magnetic field. And here, how we are able to estimate the conductivity of material. So assume that the plate is not conductive. So if the plate is not conductive, it means that we're not going to have any eddy current in the plate. And what's going to happen, we're not going to have any secondary magnetic field. But if we assume that the plate is conductive, so in that case, what's going to happen, we're going to have a secondary magnetic field. And the more conductive the plate is, the secondary magnetic field will be stronger. So by measuring the strength of the secondary magnetic field, we are able to have some idea about the resistivity of the plate. And this is how we are able to measure the resistivity of subsurface, by measuring the strength of the secondary magnetic field. As I mentioned, the device that right now in this lecture I'm going to talk about is indeed combination of two tools. One of them is SFL, or Spherically Focused log, that provides very short reading. The idea or the goal why we use this logging tool is to mostly measure the resistivity in the polyzone, the area very close to the borehole. And indeed, this device, the measurement of the resistance of this device is based on direct current into the formation. So this figure shows how this device works. As you see, this device has a central electrode, A0. Just let me highlight it for you. And this central electrode indeed sends current into the formation, central current into the formation. And then what you see here, we have several measuring electrodes, M'1, M'2, M'0, and then M0, M1, and M2. What these electrodes do is indeed they measure the potential along the borehole. And then so we have the current, we have potential, and as I mentioned, by potential over current gives resistance, and then from resistance we can obtain resistivity. So indeed, SFL measures the resistivity of the area close to the borehole. Its focus mostly is the phylloxone, the resistivity of phylloxone, or RXO. And then dual induction log, as you see here, is composed of two coils. I don't know if you can see it here in this figure. So lower coil and upper coil. And the lower coil is indeed the transmitter that produces the primary electromagnetic field. And that primary electromagnetic field induces eddy current into the formation that from the eddy current, we're going to have a secondary electromagnetic field that is recorded and detected by this coil. Just let me highlight it for you here. And this is how we are able to measure the resistivity in the Virgin zone, the area away from the borehole, and also flash zone. Just let me ask you an insightful question. Why do we use electromagnetic induction in order to resistivity of deformation when freshwater-based drill mud is used? So here is the question. Okay, so when we use electromagnetic induction, when we use it whenever the drill mud is not conductive. And so what is the reason why we have to use electromagnetic induction for the area away from the borehole? Yeah, so the answer to this question is easy, because here mud filtered is not conductive. So as a result, the area close to the borehole, I mean the flash zone, is not conductive. So if we want to direct electric current into the formation because of the high resistivity of the formation in the area close to the borehole, that current cannot get through virgin zone or transition zone. So that's the reason if we want to measure the resistivity of that area, we have to use electromagnetic waves that can go through non-conductive media. As I mentioned, in order to solve for RT's equation, there are four important resistivities. So one of the resistivities is RT, or the resistivity of the formation in the virgin zone, and another is RXO, that is the resistivity of the formation in the flash zone, and then we have RW, the resistivity of the RW, that is the resistivity of formation water in the virgin zone, and then we have RMF, that the resistivity of mud filtered in the flash zone. And from these two resistivities, RXO and RMF, we can obtain SXO, or water saturation in the flash zone. And then from RT and RW, we can estimate SW, that is the water saturation in the virgin zone. So as I mentioned here, in order to measure the resistivity of flash zone, what we use a spherically focused log that provides very shallow reading. And then this logging tool provides us with some estimate, not accurate, some estimate of the resistivity in the flash zone, or RXO. However, as I'm going to mention, it is not that accurate, and we have to combine more resistivities in order to get a more accurate estimate of RXO. So in order to estimate the resistivity of formation in the virgin zone, so we have to have deep reading. And so what we use dual induction log, and the deep reading is indicated by RID in this lecture. So something that I forgot to mention, the reading that is provided by spherically focused log, we indicated by RSFL. Okay, so RSFL is the resistivity that is provided by spherically focused log. So as I mentioned, the deep reading of dual induction log will be indicated by RID. I here stands for induction, so R means resistivity, induction, deep. So as you see here, when we have deep measurement, so this electromagnetic wave not only passes through the virgin zone, but also it passes through the flash zone, and also phylloxone. So what's happened? So this deep reading is also affected by the resistivities of, in particular, transition zone. So in order to have a more accurate estimate of the resistivity in the virgin zone, so also we have to have a medium reading that we indicated by RIM, resistivity of induction medium. And as a result, we're going to have three resistivities. So one resistivity is provided by a spherically focused log, or RSFL. And another resistivity is provided by medium reading, or RIM, another deep reading. By combining these three resistivities, as you see here, we are able to have a more accurate estimate about the resistivity of the phylloxone, or RXO, and the resistivity of virgin zone, or RT. So this is how it works. We have three measurements, and we combine these three measurements in order to have a more accurate estimate of the formation resistivities in the phylloxone and also virgin zone. Something that is interesting here, after having a lot of measurements, petrophysicists noticed that in many scenarios, RID is very close to RT. Okay, although RID is affected by the resistivity of, in particular, transition zone and also a little bit of that phylloxone, but they have noticed that in many scenarios, RT is very close to RID. So this is an important question that I may raise here. In what the geological conditions RID is close to RT? So why this question is important? Because, sometimes, as I'm going to teach you later how we can combine these three resistivities in order to have more accurate estimates of RT and RXO, but it is possible that sometimes, you don't want to do that, okay? So you don't want to go through very, challenging, maybe, corrections, or you want to use data right away to have, some quick estimate of these resistivities. Okay, guys, so one chart is available, and this chart helps us to estimate the resistivities of RIM or RID for a given RXO or RT. And as you see here, RA is the apparent resistivity that can be either RIM or RID. Okay. And here, as you see, we have another parameter that is GDI, that is a geometrical factor that is a function of the diameter of invasion zone, or DI. Okay, now just let me explain how it works. So what you see here, okay, what you see here, we have two curves. So one of them is the lower curve, or lower at the bottom, that is used in order to estimate geometrical factor for deep reading, or RID. And then we see upper curve that is used to estimate the geometrical factor for medium reading, or RIM. Here, the focus of, my focus right now is mostly to estimate the values of RID for a given the diameter of invasion zone, and RXO and RT. So now just let me give you an example how it works. So assume that RT is 10 ohm meter and RXO is 20 ohm meter and DI is 65 inches. So if we do that, and then what we want to do, we want to estimate we want to estimate RID. So from the chart, we're going to read the geometrical factor for deep reading. And if we look at this chart, we're going to notice that the geometrical factor is 0.2. And if we plug in the equation, what's going to happen? We're going to notice that RA, or the resistivity of RID, is equal to 11 ohm meter. So it is very interesting. As you see here, the actual resistivity of the formation is 10 ohm meter. But when we look at this chart, and this chart tells us that, okay, RID measurement should be equal 11 ohm meter. So from this measurement, we notice that if we want to calculate the error and assume that the error is RA minus RT over RT, the error is just 10%. So it means that the resistivity of RID is 11 and the actual resistivity is 10. And it means that RID just has about 10% of error, which is acceptable in well logging. So it means that even though if you're in a situation that you don't want to refer to the chart and just use the value of RID in order to have some estimates of RT, it is not a wrong assumption here or wrong approach here. Now just let's go through another example. So here assume that RT is 10, similar to the previous example, and RXO again 20. But here, the difference is that we assume that the diameter of invasion zone is bigger. So 230 compared to the previous example that the diameter of invasion zone was 65. Okay, guys, so if you solve for this equation, you're going to notice that here, if we want to calculate the error for RT, error will be 54%. So it means that here, if we assume that the diameter of invasion zone is big, in that case, RA, or the resistivity of deep reading, will be 15.4 ohm meter. And as a result, what's going to be have? We're going to have the error will be about 54%. That is very huge error. Now just let's go and do another example. So here assume that the drill mud is conductive, and for that reason, RXO becomes 1, RT is the same 10, but the same diameter of invasion zone that just we solved for the first example, the example that I solved it. And now what calculate the error of deep reading, or RID. So if you just solve for that equation, you're going to notice that the error will be 64%. And this is how I can calculate it. Okay, if I just want to summarize what we have learned so far is that. So in the case that the real mud is not conductive, so it means that the more pure fresh water is, it is one condition that is met. And another condition is the diameter of invasion zone. So the smaller the diameter of the invasion zone is, we're going to have more accurate reading from RID. So the condition is that 1, the remote not conductive. 2, DI should be small. In that case, what we're going to have, RID provides good estimate of RT. If these two conditions are not met, Okay, it is possible that one, the readings of dual induction logs, when the drill mud is conductive, so the readings of dual induction logs are not that reliable, so we have to use another logging tool. But now assume that the drill mud is not conductive, but has a little bit of conductivity due to the fact that fresh water have some minerals. In that case, we have to do some corrections. Another scenario is that whenever the diameter of inversion zone becomes bigger, again, it is a condition that definitely we have to apply some corrections in order to obtain a more accurate estimate of our T. Okay, guys, previously I mentioned that there are three resistivities: shallow, medium, and deep. And the goal of these three resistivities is to obtain a more accurate estimates of RXO and RT. And there are some charts available to help us to achieve this goal. And one of the charts that you see here is developed by Schlumberger. As you see here, there are two horizontal and vertical. Okay, guys, as I mentioned before, we measure three resistivities of shallow, medium, and deep in order to have more accurate estimates of RXO and RT. And there are some charts available to help us to achieve this goal. And one of the charts is developed by Schlumberger. As you see here, over the horizontal axis of this chart, in this area, you see the ratio of RIM over RID. And over the vertical axis, you see the ratio of RSFL over RID. So you may notice that how we should use this chart. First of all, we're going to calculate these ratios, RSFL over RID over the vertical axis, and RIM over RID over the horizontal axis, and find their intersection. And then what we can do. If we look at this chart, you see that this chart, there are three different curves. The first curves are the dashed blue curves. Dashed blue curves provide us with information about the diameter of invasion zone. So we can use these curves in order to estimate the diameter of invasion zone. And then you see solid red curves over which you can find the ratio of RT over RID. So what it means that once you find the ratio of RT over RID, if you multiply, so this is the ratio that you can estimate or read from red curves. And how you use it in your calculations, you can use this ratio in order to estimate RT. So how you can do that? So in order just to estimate RT, RT is obtained by multiplying RT over RID ratio that you read from the red curves times the value of RID that you read from your log data. And then in addition, you see blue curves. If you look at the blue curves here, or solid blue curve to be more precise, solid blue provides some estimates of RXO over RT. In other words, you're going to read the ratio of RXO over RT over blue curves, and just, and what you can use using this ratio, you can estimate RXO. So RXO, okay, RXO is obtained by RXO over RT ratio times RT. Just notice that you have already calculated RT in the previous step. So this is how you're using these three curves, you're able to obtain first the diameter of invasion zone, the second RT, and the third RXO. In order to better explain this chart, just let's go through this example. So assume that RID is 10 and RIM is 14 and RSFL is 90. Okay, if you do that, the first thing, as I said, you should obtain the ratio of RIM over RID and then RSFL over RID that are 1.45 and 9 respectively. And then what you do next, find intersection here. The intersection falls here. From the intersection, the first thing that I read here is the diameter of invasion zone. The intersection falls between the curve corresponds to 50-inch and 60-inch diameter. And if I just do some interpolation, I can say that the diameter of invasion zone should be about 51 inches. The second thing that I should calculate is the ratio of RT over RID from the red curves. And if you again look at it here, you may notice that in this example, RT over RID ratio is about 0.89. And the next thing from the blue curves, I should read the ratio of RXO over RT, that is here 14. So just by doing some simple multiplication, I can estimate RT here is equal to 8.9 ohm meter and RXO is 124.6 ohm meter. Okay, guys, now let's do one example here. So here, assume that RID is 10, RIM is 11, and RSFL is 30. Something that I should notice here, if the intersection falls within this area that I'm highlighting here, you see there is no red curve in the area that I'm highlighting here. If the intersection of the point falls here, it means that the red curve is 1. So what I mean that RT over, just let me write it down here, RT over RID is equal to 1 in this region. Okay, just let's do this example. Okay, if you look at it here RT is 10, RID is 28 inch, and RXO is 50. And here the intersection falls here, and I read the values of RT over RID is 1 because the intersection falls here. And as I mentioned, there is no red curve here, and within this area, RT over RID is equal to 1. DI, or the diameter of invasion zone, is 28 inches. And here, RT over RXO is 5. And this is how I estimate RXO to be 50. Here, I'm going to give you some hints about how to interpret dual induction logs. Now consider two scenarios. The first scenario is the formation is impermeable. If the formation is impermeable, it means that there is no phylison or transition zone. And as a result, I can say that RSFL should be almost equal to RIM, and that should be equal to RID. So if the formation is permeable, that means that we should have phylison and transition zone. In the phylison, the dominant fluid is non-conductive mud filtered, and in the transition zone, there is partially saturated by non-conductive mud filtered. So as a result, we should see our SFL should be greater than RIM, and that should be greater than RID. But now there are two scenarios when we deal with permeable layers. The permeable layer either is saturated by water or by hydrocarbon. And we know that the hydrocarbon is not conductive. So if the formation is saturated by water, we should expect low resistivity in the virgin zone. So if it is saturated by water, we should see low RID. But if the formation is saturated by hydrocarbon, okay, hydrocarbon is not conductive, in that case, we should expect high value of RID. So in other words, the major reading that help us to identify hydrocarbon saturated zones is RID, because RID provide us with information about virgin zone. So if the virgin zone is saturated by water, it should have low resistivity. And on the other hand, if we have some hydrocarbon in the formation, it means that the hydrocarbon is not conductive. So RID should be a high number because it shows high resistivity. Now let's do this example. As you see here, you're given two different data, logging data, SP log on this track. And then you have dual induction log data on this track. First, find permeable layers and then hydrocarbon saturated layer. So it is not that hard to identify impermeable layers. By looking at SP log data, we can easily identify permeable and impermeable layers. I mentioned that whenever SP log is positive, so that zone should be impermeable. So you see two zones with positive SP. So this zone and this zone, these two zones are impermeable zones. And also we see two zones with negative SP, this zone and this zone, that we can consider to be permeable zones. Okay, now another question was to identify hydrocarbon saturated zone. And I mentioned that if we want to identify hydrocarbon saturated zone, so we should look at deep reading, RID. And here, if you look at RID, you see that in this zone, the lower zone of this permeable layer, RID is very low. So I assume that this zone should be saturated by water. But at the upper part of this permeable zone, you see that RID increases. An increase of RID can be an indicator of hydrocarbon saturation. So what I can do here, I can say that this zone should be saturated by hydrocarbon. As you see, by looking at the speed log data, I was able to identify permeable and impermeable layers. And by looking at resistivity data, I was able to identify hydrocarbon saturated zone. But here I want to mention something, that resistivity data can also provide us with some information about the state of permeability of layers. And here is interesting that if you look at this zone, let me highlight it here. In this one, you see these three curves are separated from each other, the three resistivities. It means that these three resistivities are not equal. RSFL is not equal to RIM, and that is not equal to RID. And I mentioned that happens only in permeable zones. And what I can say that this is a very, very thin permeable zones that lies within an impermeable layer. Because this zone is so thin, it is very hard to identify it by looking at SP log data, because SP really provide us with very low resolution. But here, resistivity log has been able to identify this zone. So it means that we can also use resistivity data in order to identify permeable or impermeable layers. One of the corrections that we may have to apply is borehole effect. And what is that? In the case that the drill mud is not conductive, it means that the drill mud is made from purely fresh water. In that case, we don't need to have applied this correction. But in the case that the drill mud has a little bit of conductivity, for example, there are some small fractional minerals in the fresh water, and for that reason, the fresh water is conductive. So in that case, we may apply this correction. And in order to do so, first we have to calculate the borehole signal. The borehole signal is a function of three parameters, as you see here. The first parameter is the resistivity of drill mud. The second is the borehole diameter. And the third is standoff of logging tool, the distance between the logging tool and the borehole wall. And as you see here, a chart is available to estimate the borehole signal. And how we can do that, as you see there on this chart, there are some solid blue curves that are used to calculate the whole signal for deep reading, and the dashed blue curves are used to calculate the whole signal for medium reading. Okay, guys, so now just let's do an example about how we can use this chart. The first thing that you should find on this chart is the hole diameter. Assume that here the hole diameter is 14.6 inch. And the first thing, we're going to draw a line to cut one of these curves. So assume that we want to estimate the whole signal for deep reading, and the standoff distance is 1.5 inch. So we're going to draw a line to cut this curve that corresponds to the standoff of 1.5 inch. And then from this point, we draw a perpendicular line to cut the vertical axis. We find this point on the vertical axis. At the same time, what we're going to do here, on the middle stem here, we find the resistivity of drill mud. For this example, we assume that the drill mud has the resistivity of 0.35 ohm meter. So we find 35 ohm meter here. And from this point, we draw a line that crosses over this point, the resistivity of drill mud, to cut the whole signal axis here. And on this axis, we can read the whole signal. Something that is noticeable here is that the whole signal, the unit of the whole signal is millisiemens per meter. That is the unit of conductivity. So if we want to apply correction to our data, deep reading or medium reading, so the first thing that we should do, we should convert the resistivity to the value of the conductivity. How we are able to do that? The first thing that we want to do here, we want to convert the resistivity to conductivity. What we want to do in conductivity, we want to have conductivity in millisiemens per meter. So in order to do so, as you see here, what we do here, we divide 1000 over RIM to convert the medium resistivity to medium conductivity. But the unit here is millisiemens per second, and that's the reason why we use 1000 here. Or for deep reading, we do the same thing, 1000 over deep reading. And then once we do that, the corrected conductivity is either RIM or CRIM, which means that the conductivity of medium reading, or CRID, or the conductivity of medium reading minus the whole signal. So this is how we obtain the corrected conductivity. And once we obtain the corrected conductivity, then again we convert corrected conductivity to the corrected resistivity. So how we do that? The corrected resistivity RC is given by 1000 over corrected conductivity. So now let's go back to the example. So in the example, assume that the whole signal is, assume that the deep reading RID is 50 ohm meter. And I mentioned that the whole signal, if we go back here, was 5.7 millisiemens per meter. And so what we should do, 20 minus 5.7 is going to be 14.3 millisiemens per meter. And then the corrected resistivity is 1000 over 14.3. That is equal to 69 ohm meter. So what you see here, without calculating or without considering the whole signal, the deep reading was 50, but after considering the effect of the whole signal, we obtained 69 ohm meter. That means the whole signal causes some underestimation of deep reading. Now just let's do another example here. Assume that we have the borehole with the diameter of 14.6, the standoff is 1.5, and the drill mud resistivity is 0.35. So how much is the whole signal for the medium reading? Okay, guys, so for the medium reading, we should use the dash curve. And if we use the dash curve, then we're going to see that the whole signal for deep reading is 22.5 millisiemens per meter. Something that is noticeable here, and you should notice, is that our reading of deep or medium readings are reliable as long as the conductivity of deep or medium reading is much greater than the whole signal. Okay, so whatever value that you get from the whole signal, you can calculate it and then compare it with the conductivities of deep or medium reading. If the value of the whole signal is much smaller than those conductivities, then what we can say that the readings of medium and deep readings of dual induction logs are reliable, and we can use them in our calculations. Otherwise, those readings are not reliable. In that case, we have to go back to the company or contractor and ask them to use another logging tool that I'm going to talk about it in the next video. And that is logging tool is dual ladder log that are used whenever the drill mud is conductive. Okay, so what I'm saying that in the cases that the drill mud is conductive, is highly conductive, the whole signal will be significant. And in that case, the data from dual induction logs are not reliable, and we have to use another device. So now assume that RIM is 50 ohm meter and the whole signal is 90 millisiemens per meter. So here is the question: is the measured RIM reliable? Okay, guys, as you see here, if just I want to calculate the whole signal here, the whole signal is 90 and the conductivity CIM is 1000 over 50 or 20 millisiemens per meter. So from this example, you see that the conductivity is very close to the whole signal. And what I can conclude is that this reading is not reliable, and we cannot trust the data. So we have to use another device for measuring the resistivity of the borehole, that is dual ladder lock, that I'm going to talk about it in the next session. I hope that you have enjoyed the lecture. And as I said, this logging tool is one of the resistivity logging tools that we use in order to measure the resistivities of formations. And when we use this logging tool, we use this logging tool for the case of non-conductive drill mud. And the logging tool mostly works based on induction principles. Thank you very much for your attention.